あとは音楽。あれ流れないぞ。なんでだ？こっちか。Let's see. Monitor and output. Ah, hi. There we go. So I'll throw this on the left screen. 音楽だけ下ろしてね。どうやるんだこれ。もうちょっと低い方がいいか。こんな感じかな。汚ねえな。どうすんだこれ。Stream health. Okay, so I can see the stream health now. And I'm gonna be sitting around here, so let's do it like that. Likeやっぱやりづらいな。There we go. Okay. So I'll throw this in the corner. Yeah. And we'll do it like this. Okay. The music sounds fun. I need some water. My throat is like dead. Okay. And let's see. Yeah. Top left corner will be okay. It's too small for anyone to see. And okay, so we'll just check bandwidth usage and stream stability for today. Sounds about right. That's mainly because I have to do this anyway to finish my assignments, but you know. Okay. Alright. Yeah, it's too small to see. Okay, perfect. Alright, so, well, where was I even at? So we computed lambda for, or we could have computed our eigenvalues, we'll call it for that. So for lambda equals 0, we have the vector v1 equals 1, 1, 1. For lambda equals 4, we have the eigenvector v2 equals 3, negative 1, 2, negative 2. So now we want to use lambda equals 18, right. Man, my throat is dead. Okay. So we end up with, let's double check. Yeah. No, it's not XYZ, it's X1, X2, X3. あ、タイトルも英語入れといた方がいいかな。入れといた方がいいか。There. Right, and then we'll do, how do I save settings? How do I save settings? How do I? Do I just not have a way to change the title during stream? Yeah, okay, sure. Sucks, but whatever. Yeah. Alright. Alright, so 3x1 minus 3x2 equals 18x1. We'll have negative 3x. I'm gonna replace that in the microphone. There. Yeah. Negative 3x1 plus 11x2 minus 8x3 equals 18x2. And we'll have 0x1 minus 8x2 plus 8x3 equals 18x3. So we'll take equation 1, bring it over here, and say 3x1 minus 3x2 equals 18x1 implies that, okay, well, we'll do. That implies negative 3x2 equals 15x1. So let's see what we're doing in terms of x1. So x2 is equal to negative 5x1. Yeah, that sounds right. Okay, so we'll have that relationship. We'll take the second equation for convenience. We'll say that negative 8x2 plus 8x3 equals 18x3. That implies that we'll keep a negative 8 on this side, so we'll have negative 8x. Yeah, we'll put x3 on the left side for convenience. So that'll be negative 10x3 equals 8x2. x3 is then negative 4/5 x2. That sounds about right. Okay. So it will be a convenient number for us. If x equals 1, okay, so we'll just say let x equal 1, then, or x1 equal 1 rather. And then x sub 2 equals negative 5, and x sub 3 equals negative, well, positive 1 actually. That sound right? x1, 5, 5, doesn't sound right. If x1 equals 1, and then x2 equals negative 5, that's negative 5, then this should be 4. Why did I say 1? Oh, my avatar is totally out of center, or off center. There we go. Okay. Yeah, okay, that's fine. Alright, so, if I plug in 4, does that make sense then? x3 is 4, so that's going to end up with a negative 24. We'll have a negative 24 and a 27 and a 5 there. Doesn't sound right either. Negative 55, a 4, and a 3. Okay, yeah, no, something doesn't sound right. Something doesn't sound right. What did I do wrong? So we have 3, negative 3. Yeah, so put the negative over here. Divide by negative 3. You get a negative 5, yeah. Yeah, for x2. This is negative 8 x2 We're going over this positive. That's part of 8x. Take away the 18, you do get negative 10x, x sub 3. So 8 divided by 10, well that's obviously 4/5. Yeah. So then x equals... Why doesn't this make sense? Yeah, right, because, well, negative 3x1, we're going to put x1 there, plus 11x2 minus 8x3 equals, 18x2, that's what I was forgetting, so let's double check and make sure that makes sense. So we have negative 3 then, we have a positive 55, we have a, what is this, negative 32? Negative 32. Yeah. And that should equal 18 times 4, which is, what, 72? There we go, that seems wrong too. x2 is, that's not right actually. Wait, what am I doing wrong? So, x1 equals 1, so that should be negative 3, that's fine. x2 then ends up being negative 5, which will generate a negative 55 there. Negative 55 rather. Negative 55. And then negative 8x2, or x3 rather. Negative x3, which is a negative 32, that's 35 and 55. 18 x2 is negative 5, so that ends up being a negative 90, 80, 90, yeah, okay, yeah, that's right. Okay. So, yeah, so, let's see. So, our vector v sub 3 is equal to the vector 1, negative 5, 4. Yeah. Yeah, okay. Alright, what else did they want? Let's see, find the eigenvalues and eigenvectors. Okay, so, let's see. So, in conclusion, the eigenvalues and corresponding eigenvectors of M are, I'm not gonna think about what time is it in Japan right now. Yeah, well, I mean, time's about right. It's probably just too many popular VTubers. Yeah, whatever. I mean, I think it's a good time to start homework, so hopefully some gullible person shows up. Okay, so what was I saying? Yeah, I want V1, lambda equals 0, or what did I put lambda equals 0? Lambda equals 0, V1 equals 1, 1, 1, so our, let's see, lambda sub 1 equals 0, V sub 1 equals 1, 1, 1. Yeah. And we have lambda equals 4, or lambda sub 2 equals 4, I guess. Oops. I'll write them vertically for convenience, actually. Lambda sub 2 equals 4, v sub 2 equals, where is it? Oh, there it is, 3, negative 1, negative 2. 3, negative 1, negative 2. Right. And lambda sub 3 equals 18 with v sub 3 equal to 1, negative 5, 4. Okay, so those are our eigenvalues and eigenvectors of M. And, right, so next part is part D. I forgot what D is probably placed at around that position. Okay. So use the result in part C to find the resonant frequencies omega. Okay, so using lambda equals, where is it? Oh, here it is. Using lambda equals m omega squared over k. Do I even need to plug in anything? Yeah, no, I can just use it, so. Okay. Let's see. For lambda equals 0, we have 0 equals m omega squared over k, and I don't think we're given the mass or the spring constants. Equal masses, 3 equal masses, and omega squared, k is just some spring constant, and we've done everything in terms of the spring constants and the masses, so that shouldn't matter. Okay, so then yeah, well, that doesn't really make much sense. What could I be missing? Just plug in that. I guess the resonant frequency. Well, can you have a resonant frequency of 0? That doesn't sound right. Let's see what everyone else said. Okay, someone does argue that the resonant frequency is equal to 0, so yeah, okay, sure. I mean, it seems kind of weird, but I suppose that's a angle in radians, so we would say that repeats every... Oh, there we go, okay. There. Alright, so 0 equals omega, or m omega squared over k, so then 0 equals omega squared, omega equals 0. For lambda equals 4, we have 4 equals m omega squared over k, so that's 4k over m equals omega squared, or 2 times square root k over m equals omega. That's for other resonant frequency. And for lambda equals 18, we have, let's see, 18 equals m omega squared over k, and we'll do 18k over m equals omega. So that's 9 times 2, so that's going to be 3 square root 2. I guess for 2k over m. Yeah. 3 square root 2. Yeah, it's kind of a weird number, isn't it? Whatever. 3 square root. Can't write a square root today, apparently. 2k over m. Yeah. Equals omega. Yeah. Let's see if anyone else simplified it. Not really, but whatever. Yeah. That seems about right. Okay. Yeah. So, let's see. I guess I should just say, so, resonant frequencies are omega equals 0, 2 rad k over m, and 3 rad 2k over m. There. That's a good finish. Okay. Let's see, homework set. Alright, homework set 4, part 3. Let's see. Okay. Homework set 4. Let's see, that's gonna be problem 3. And, yeah, okay. So let v1, v2, v3 be the three eigenvectors of the symmetric matrix. Okay. Show that v1, v2, v3 are orthogonal. So let's just let's write our givens first. It's going to be v1 equals 3, 1, negative 1, 5. Let's see. v2 equals 3, 1, 5, negative 1. v3 equals 1, 1, negative 1, negative 1. And M is our entire nasty matrix. There, so negative 3, 6, 0, negative 3, 6, negative 7, negative 3, negative 4. I don't have enough space. Negative 3, 6, 0, negative 3, 6, negative 7, negative 3, negative 4, 0, negative 3, 1, 2, and negative 3, negative 4, 2, negative 3. Okay. Good. Right. Okay, so we want to show that part A, that v1, v2, v3 are orthogonal. Okay, so just take the dot product of each. So it's going to be v1 dot v2, which equals 3, 1, negative 1, 5, dotted with 3, 1, 5, negative 1, which equals corresponding components multiply, so that's going to be 3 times 3 plus 1 times 1 plus negative 5 times, or sorry, negative 1 times 5, negative 1 times 5 plus 5 times, I can't seem to be consistent with my notation today. Negative 1 times 5 plus 5 times negative 1, which equals 9 plus 1 minus 5, which equals 0, so it checks out. Okay, we'll do v2 dot v3, v2 dot v3, which equals, here we go, that's going to be 3, 1, 5, negative 1, and 1, 1, negative 1, negative 1, which equals 3 times 1 plus 1 times 1 plus 5 times negative 1 plus negative 1 times negative 1, which equals 4 plus 1 minus 5 plus 1. That doesn't sound right. Why did I do 4 there? It's 3. Dur. Oh, arithmetic. There we go. So that equals 0, which checks out. Let's check something first. Okay. So we'll do v1 dot v3, which equals 3, 1, negative 1, 5, and 1, 1, negative 1, negative 1 equals. And then we'll do 3 times 1 plus 1 times 1 plus negative 1 times negative 1 plus 5 times negative 1, which equals 3. Keep trying to write 4 for some reason. 3 plus 1 minus 5, which equals 0, checks out. Therefore, v1, v2, v3 are orthogonal. Okay, that's fine. B now. Find the fourth eigenvector of matrix M. Said something about row and span. Find the 4 eigenvalues. See if anyone has tips for problem 3. Problem 3. Hmm. 子供かよ、ほんと。あ、そういうことか。So that's the wrong measure of conical axis, do you think? Okay, let's see. Ah, そっちじゃねえわ。これか？ Maybe I really should blur the... Actually, I can just show it off screen now that I think about it. That'll be fine. Let's see, so... Let's see. Eigenvalues. Alright, so definition of group. A group is a set ABC of elements which be a member, combination of two elements, term properties of combination. Did we even talk about this? Conjugate elements in class. Character. Infinite groups. General vector spaces. I guess we did talk about this, didn't we? Let's see. Is it? Yeah. Okay, so find the fourth eigenvector. And what do we say? I mean, honestly, it'd be faster to just find all the eigenvalues and then... So I guess how do I work backwards from here? If I got v1 equals this, that effectively means... Maybe? Like 3x1, 1x2, negative 1x3, and 5x4, right, effectively? So... Oh, let's look in the textbook. I don't know. Let's see. This is too far past. I mean, honestly, isn't it faster to just find the eigenvalues first? Hmm. Let's just turn up the audio real quick. Oh wait, that doesn't matter. I guess ほいっと。はい。
A be the following 3x5 matrix. Find a basis for the null space of A. First, definition. The null space of A is going to be a set of all vectors in R5 such that when we apply A to our vector, out comes the 0 vector. And this 0, 0 space. Echelon flows. I'll say more about what happens with those vectors.
So I guess row reduction should just work then. Okay. Let's try that then. We'll do -3, 6, 0, -3, 6, -7, -3, -4, 0, -3, 1, 2, and -3, -4, 2, -3. And I guess if I row reduce this, I should get a... That doesn't really sound right, but... No, let's let the video play a little more.
If you notice, we get nice separation here. I have dependent variables on this side and only independent variables on the right-hand side. That's because I use reduced row echelon form. If you don't, you'll get some mixing on the right-hand side, dependence and independence. Now, how do we get the basis? So what we're going to do is we're going to take each independent variable, pick one, set it equal to 1, set the rest equal to 0. That's going to tell me how to fill in a vector. So what do? If I let x3 be equal to 1, x5 will be equal to 0. So those are the independents. Then when I use the equations, what comes out is the vector -3, -1, 1, 0, 0. That's my first basis vector. Then we just proceed. We'll go through all of our independent variables in that manner. So our next one, I let x5 be equal to 1, I let x3 be equal to 0, and then we just see what the equations give us. So we'll get 5, 4, 0, -3, 1 for my second basis vector. Now, that's our basis. So,
okay, sure. Let's see, matrix, or actually Mathematica. Okay, new notebook. We'll do m equals quantity, and then 1, 2, 1, 2, 4. Okay. We'll do -3, 6, 0, 3, -3 rather. -3, 6, 0, -3, yep. 6, 7, -7, -3, -4. Here, 6, -7, -3, -4, 0, -3, 1, 2, and -3, -4, 2, -3. Okay. And if we do row reduce, matrix M in matrix form, let's see, so we get everything kind of, okay, I see what happens. Okay. Okay. Excuse me. Let's see, so we're going to do row reduction. So that's going to be -3, 6, 0, -3, 6, -7, -3, -4, 0, -3, 1, 2, and -3, -4, 2, -3. Okay. And we'll just start row reducing. Yeah. Excuse me. Excuse me. We'll do -3, row 1. Anything else that divides nicely? No. Alright, nothing divides nicely. That's fine. Do 1, -2, 0, 1. And 6, -7, -3, -4, 0, -3, 1, 2, and -3, 4, 2. Well, actually, we could have done more steps there. Probably could switch row 2 and row 3. Actually, move around a bunch of rows, actually. Yeah, sure. I don't know, actually. Yeah, we'll leave it, actually. We'll leave it. It's 1, -2, 0, 1, 6, -7, -3, -4, 0, -3, 1, 2, and -3, -4, 2, -3. Alright. There we go. Step 1. Next step, we'll do another side of the page, I guess. Oh, you know, am I using the wrong microphone? Okay. There we go. Okay. See, I keep making that mistake. Probably made it unbearable to listen, but hopefully that's fixed now. Hopefully. Okay, yeah. Okay. So let's do the next step, which is oh, here's a matrix. B, it's about this far away. Let's draw a little smaller. 1, -2, 0, 1, 6, -7, -3, -4, 0, -3, 1, 2, and -3, -4, 2, -3. Yeah. Okay. So let's let's use our 1s now. So we're going to do negative 6 R1 plus R2 store R2 and 3 R1 plus R4 store R4. There we go. Okay, so we're keeping our row 1, that's 1, negative 2, 0, 1. Okay, and we do negative 6, so that's going to be negative 6 and 6, that's 0, that's going to be negative 6, so positive 12 and negative 7, that's going to be a positive 5, 0 and a negative 3, that's going to be a negative 3, and a negative 6 and a negative 4, that's going to be a negative 10. Yeah, alright. Next one, so we have 0, negative 3, 1, 2, and we have 3 and negative 3, that's going to be 0. We have a negative 6 and a negative 10, that's going to be, or negative 4, that's going to be negative 10. A 0 and a 2, that's going to be 2. And a 3 and a negative 3, that's going to be 0. Oh, perfect, perfect, perfect. Is it perfect? Is it? 1 and 5. Interesting. Okay, so what should I make our 0 row? Okay. Can I make a 4 somewhere? I can make a 5 and a 0, but 3 and okay, here we'll do that. We'll do that. 3 and 9, 2 and 3, 3 and 2, 7, 8. No, okay, yeah. So we'll do negative 3, row 3 plus row 4, store row 4. That's what we'll do. That'll generate a nice one. So 1, negative 2, 0, and 1. We have a 0, 5, negative 3, negative 10. We have a 0, negative 3, a 1, and a 2. And now we have a 0 and a negative 3 times 3, that's 9, minus 10, that's going to be negative 1. We have negative 3 and 2, so that's going to be negative 1. We have negative 3, so negative 6, and a 0, so that's going to be negative 6. And then we'll say, what should we do now? Cayena. Okay. Yeah. Pop, pop, pop. Okay. We'll do a, is there anything else I should do first? No, I guess not. So then we'll just make this the new row 2. So we'll do, row 2, switch with row 4. 1, negative 2, 0, 1, 0, negative 1, negative 1, negative 6, and 0, negative 3, 1, 2, and a 0, 5, negative 3, negative 10, negative row 2. Yeah, that'll be good. Yeah, I'll just do it now, yeah. 1, negative 2, 0, 1, 0, 1, 1, 6, 0, negative 3, 1, 2, and 0, 5, negative 3, negative 10. There. Okay. Now we can do all the rows, so that'll be 2, row 2 plus row 1, store row 1, 3, row 2 plus row 3, store row 3, and negative 5, row 2 plus row 4, store row 4. Okay. 1, so that's going to be 2, so 0, it's going to be 2 and 0, so that's going to be 2, and then going to be 12, and 1, that's going to be 13, 13, what? Anyway, 0, 1, 1, 6, that's going to be 0, so it's going to be 3, and 2, 2, 2, and 12, yes, okay, yeah. 3, that's going to be 0, and 3 and 1, that's going to be a 4, that's going to be 3, so 18 and 2, that's going to be 20. Oof. Oh, that's where the 0 comes from. Okay, that's good. That's good. That's good. 0, we have our -5 and a 5, so that's going to be a 0, a -5 and a -3, that's going to be a -8, a -30 and a -30 and a -10. -30 and a -10, that's -40. Okay. Flip page. Okay, so we continue on with our matrix 1, 0, 2, 13, 0, 1, 1, 6, a 0, 0, 4, 20, 420 blaze it, no, anyway, -40, and then we'll say, -2, or not -2, +2. +2, R3 plus R4, store R4. That's going to get rid of our 4th row. So we get 1, 0, 2, 13, 0, 1, 1, 6, 0, 0, 4, 20, and 0, 0, it's 8 and -8, 0, negative, or +40 and 40, that's going to be 0. Okay, and next what? I guess quarter row 5, so 1/4 row, no, row 5, what am I saying? Row 3. Yeah. 1, 0, 2, 13, 0, 1, 1, 6, 0, 0, 1, 5, 0, 0, 0, 0. Yeah. Okay. So we'll do negative row 3 plus -2 row 3 plus row 1 store row 1 and -1 row 2 plus row 1 store. Huh? What was I? -2 row 3 plus row 2. -2 row 3 plus row 2 store row 2. Okay, so those are my daily annihilation awards, or rewards rather. Okay, and then I just finish up my what do I need, like EXP? Yeah, sure. And supplies, I don't know. Some EXP, some supplies. There. Alright. Okay. So 0, 0, -2, so row 3, so that's -2, 2, that's going to be 0, that's going to be -10 and a 3, that's going to, or -10 and a 13, that's going to be 3. We have 0, 1, -1 and 1, that's going to be 0, and a -5 and a 6, that's going to be 1. We're going to have 0, 0, 1, 5, and 0, 0, 0, 0. So that implies that... okay. So that implies multiplying this by x1, x2, x3, x4 equals 0, that x1 plus 3x4 equals 0, x2 plus x4 equals 0, and and x3 plus 5x4 equals 0. So we can make it all in terms of x4, I guess. Yeah, okay. So for convenient, let x4 equals 1. Then actually, let's do it in terms of x4. So okay. So that implies that x4 equals 1/3 x. No, I should just do it in terms of x4. Yeah. So x1 equals -3 x to the 4, or x sub 4. There. x2 equals -x4. x3 equals -5 x4. Yeah. So if we let x sub 4 equal 1, then x sub 1 equals -3, x sub 2 equals -1, x sub 3 equals -5. So, wow. Yeah, okay, sure. So then, v sub 4, I guess. Just realized I'm probably out. Yeah, I'm out of lead. There. So v equals, what was it? -3, -1, -5, 1, or 3, 1, 5, -1 for convenience. Okay. Wait, no, that doesn't sound right. This is the same vector as v sub 2. -3, -1, -5, and the last vector would be whatever we want. So it has to be the last vector. And that's the same as the... Oh, I still need to mute this. How do I do that? Did I write down the matrix wrong, maybe? That's -3, 6, 0, -3, 6, -7, -3, -4, 0, -3, 1, 2, -3, -4, 2, -3. That's right. Yeah. Matrix is symmetric too. Yeah. Okay, I'll have to stop the stream again or kind of mute it. And boop. There we go.
So the number of vectors we'll have in the basis is the number of independent variables. As a check, what you can do is take your original matrix, apply it to each basis vector. What you expect is you get 0 out. So if I take our original matrix times -3, -1, 1, 0, 0, you'll note when you work it out, you get the 0 vector. Similarly, we apply our matrix A to 5, 4, a vector. So
Okay. So I don't get how this happened, but how did you get x2 for that? have a... Say they got like 3, 5, 1, -1, I guess. Wolfram Alpha corroborates the null space. Someone give me clue 3. Oops.
Probably occur over several videos is really integrate everything we know about matrices and null spaces and column spaces and linear independence. So I have this matrix here, this matrix A, and I guess a good place to start is let's just figure out its column space and its null space. And the column space is actually super easy to figure out. It's just the span of the column vectors of A. So we can right from the get-go write that the column space of our matrix A. Actually, let me do it over here. I can write the column space of my matrix A is equal to the span of the vectors 1, 2, 3, 1, 1, 1, 4, and 1, 1, 4, 1, 4, 1, and 1, 3, 2. I'm done. That was pretty straightforward, a lot easier than finding null spaces. Now, this may or may not be satisfying to you, and there's a lot of open questions. Is this a basis for the space? For example, is this a linear independent set of vectors? How can we visualize the space? And I haven't answered any of those yet. But if someone just says, hey, what's the column space of A? This is the column space of A. And now we can answer some of those other questions. Is this linear? If this is linearly, if this is a linearly independent set of vectors, then this would be a basis. These vectors would be a basis for the column space of A. We don't know that yet. We don't know whether these are linearly independent. But we can figure out if they're linearly independent by looking at the null space of A. Remember, these are linearly independent if the null space of A only contains the 0 vector. So let's figure out what the null space of A is. And remember, we can do a little shortcut here. The null space of A is equal to the null space of the reduced row echelon form of A. And I showed you that when we first calculated the null space of a vector, because when you perform these, essentially if you want to solve for the null space of A, you create an augmented matrix and you put the augmented matrix in reduced row echelon form, but the zeros never change. So essentially you're just taking A and putting it in reduced row echelon form. So let's do that. So I'll keep row 1 the same. 1, 1, 1, 1. And then let me replace row 2 with row 2 minus row 1. Row 2 minus row 1. So what do I get? 2, 1 is minus 2. And 2, so minus 2 x 1, any member of the real space. So all solution set in my null space is going to be a linear combination of these two vectors. And we can figure out what these two vectors are just from these two constraints right here. So let me do it in a neutral color. x1 is equal to minus 3 times x3, so minus 3 times x3 minus 2 times x4. Straightforward enough. x2 is equal to 2 times x3 plus x4. What's x3 equal to? Well, x3 is equal to itself. Whatever we set x3 equal to, that's going to be x3. So x3 is going to be 1 times x3 plus 0 times x4. It's not going to have any x4 in it. x3 is going to be kind of an independent variable where it's going to be free. We can set it to whatever it is. So we set it, and then that's going to be our x3 in our solution set. x4 is not going to have any x3 of these two guys. The span of minus 3, 2, 1, 0. And let me scroll over a little bit. And minus 2, 1, 0, 1. Now, let me ask you a question. Are the columns in A, are they a linearly independent set? Are they a linearly independent set? Let me write that down. So if we write these vectors right there, these are the vectors, the column vectors of A. Right, so let me write that down. So are the column vectors of A, so what were they? Let's see, 1, 1, 3, 2. I don't remember them. It's 1, 2, 3. 1, 2, 3, 1, 1, 4, 1, 4, 1, and 1, 3, 2. So this is just the column vectors of A. I could just write A as just this much of columns, but my question is this a linearly independent set? Let me just write it like this. A is equal to this, not just one solution. Obviously, 0 vector is contained here. If you just multiply both of these, if you pick 0 for that and that, it's contained, but you can get a whole set of vectors. So because the span of this guy, so you can kind of, the null span of A, the null space of A does not just contain the 0 vector. So it has, more than just 0, more than just 0. So what does that mean? Well, that means that there's more than one solution of this, and that means that this is a linearly dependent set. Linearly dependent set. And what does that mean? Well, at the very beginning of the video, I said, what's the column space of A? And we said, oh, the column space of A is just the span of the column vectors, right? And I just wrote it out like that. And I said, well, it's not clear whether this is a valid basis for the column space of A. And what's a basis? A basis is a set of vectors that span a subspace, and they are also linearly independent. And we just showed that these guys are not linearly independent. Not linearly independent. So that means that they are not a basis. Guy can be represented by some combination of these two guys, and by the vectors that on what is minus. Well, then go. Okay, let me scroll to the vector, and you can even verify it. 2 times 1 minus the set that this 0 and x4 equal to. Again, we can just solve for our x1s and x2. If x4 is 0 and x3 is minus 1, then x4 is 0, so x3 is just minus 3 times x3. So x1 would be equal to 3, right? Minus 3 times minus 1. And what would x2 be equal to? x4 is 0, we can ignore that. x2 would be equal to minus 2. So this would be 3, and then this would be minus 2. Let's see if it works out. 3 times 1 minus 2 is 1. 3 times 2 minus 2 is 4. 3 times 3 minus 8 is 1. It checks out. So I'm able to write this vector as that was associated with a free variable as a linear combination of these two. So we can get rid of him from our set. So now I've shown that this guy can be written as a linear combination of these two. This guy can be written as a linear combination of these two. So the span of all of those guys should be equal to the span. So let me write it this way. All right, cross that guy. The column space of A, I can now rewrite. Before it was the span of all of those vectors. It was the span of all of the column vectors. V1, V2, V3, and V4. Now, I just showed you that V3 and V4 can be rewritten in terms of V1 and V2, so they're redundant. So that is equal to the span of V1 and V2, which are just those two vectors. Vector 1, 2. And then this problem is row 1. And this minus 2 plus x4. Our system of equation like this, and we put it into reduced row echelon form. So these are the null space of the reduced row echelon form of A, right? So here all of the x's, this is the null space. This problem, if we find all the solution set, all of the x's here, this is the null space of the reduced row echelon form of our matrix A. But we're saying that this problem is the same problem as.
That's good morning.